Welcome back, everyone. So today I'm going to start a mini lecture series on complex analysis, which is essentially the study of numbers and functions of complex variables z, where z has a real part and an imaginary part. We write this usually as x plus iy. X is real, y is also real, but iy is imaginary. And in my kind of college math class, this would usually take up about 2 weeks, the series I'm about to give you right now. I think I'm hoping to do this in about 12 or 13 little mini lectures. I'm really hoping it ends up being 13. The inauspicious and occasional number of lunar months that fit into a solar year. Okay, so complex functions and complex variables come up all the time in differential equations, ordinary differential equations, ODEs, like when we deal with pendula swinging, or if we have a mass on a spring that is oscillating. Pretty much anything in physics that oscillates, that moves back and forth, is going to involve some kind of complex function. Usually we think of this motion as periodic, so it's going to be described by sines and cosines. And what we're going to see very, very quickly is that sines and cosines are actually the imaginary and real parts of a complex exponential function. So very cool stuff. Good. Now, when I start, I like to kind of define what I mean by I, this imaginary number. Most of you know this from high school or grade school. You've seen this before. We say that I equals or is defined as the square root of -1. So we know what the square root of 9 is. It's 3. But it could also be -3, because -3 times -3 is +9. And very quickly in school, you realize that these negative numbers don't have a real valued square root. There's no real number that when squared will give you a negative number. And so you have to introduce this imaginary, this I, this other variable I, that is defined as the number that when squared equals -1. This has bothered humans for centuries, all the way back in the 1500s. Actually, I think all the way back to Alexandria, it was recognized that you needed other numbers to take these square roots. But especially in the 15, 16, and 1700s, lots of mathematicians really wrestled with what this meant. They didn't like this number. Descartes called this imaginary in kind of a derogatory way. And it wasn't until Euler and Gauss, a bit later, that this really started to become an established part of mathematics. And if you think about it, even negative numbers for a long time were not really seen as real. I could, of course, owe someone, 5 apples, which is kind of like -5 apples. But, the idea of multiplying 2 negative numbers and getting a positive number is still kind of unintuitive for kids. You need to get a lot of intuition and build up a lot of experience of how numbers work and how subtraction works before you can make that leap. And this is kind of the same way. But I want to point out that this is very much not an imaginary number. In my mind, these are extremely concrete quantities, again, that are everywhere in our solution to ordinary and partial differential equations. So I'm going to walk you through bit by bit, piece by piece, how to think of complex variables, how to think of complex numbers, and functions of these complex variables. And we're going to use these over and over again in differential equations, to solve the wave equation, the heat equation, spring mass system, things like that. Now, in the Bronze Age, when I went to school, this whole series on complex analysis would have been an entire 10-week class. There is a huge amount of depth that you can study complex variables. In my class that I teach to my students at University of Washington, I've condensed this down to 1 week of essential material and then 1 week of kind of extra advanced material that I think most students should know. It's almost like you take art and history classes so that you have a well-rounded education, kind of a liberal arts education. I almost think of complex analysis that second week as like a liberal science education. It's something that people should know, even if we don't use it as much as we did 50 years ago. Okay? Good, so I'm going to keep going through this. So we're talking about these complex numbers that have a real and an imaginary part, and we have defined this imaginary number I as the number that when squared equals -1. So it is the solution to the polynomial equation x squared equals -1. And again, for a long time, people realized that there are polynomials you can write down that don't have real valued solutions. Okay, this bothered people for hundreds of years. There's actually a great Veritasium video on the history of the imaginary number. I'll put a link in the description below. But it was recognized at some point down the line, I'm guessing probably Gauss formalized this, that you need these imaginary numbers to write down the solution of a generic polynomial. So if you have any polynomial I can write down, its solution, the roots of that polynomial, will generically need complex valued numbers to express those roots. For example, this is a polynomial where x has to equal I or minus I to satisfy this polynomial. Okay, and so in some sense that means that these imaginary numbers are necessary. So if we want all of the solutions of these polynomials, then we need these complex numbers to represent these solutions. And it wasn't until quite some time that people also proved that these are sufficient. I can write down any polynomial, any real coefficient polynomial, and I can represent all of the solutions in this form. So that means that I don't need some other variable plus jz, where j is some other quantity to represent the solutions. A real and an imaginary valued number like this is sufficiently rich enough to capture the solution of all polynomials. And in fact, that's even true if I had complex coefficients on these polynomials. If I had I times x squared equals -1, that would also have roots that are representable by complex numbers. So that's kind of an interesting and important mathematical fact, that these numbers are necessary to represent the roots of polynomials, but they are also sufficient. They are a rich enough class of numbers. We would say that the solutions of these polynomials are closed under the complex numbers. Okay, good. So we know that these come up all the time in ordinary and partial differential equations, things like this. I'll also write down that these are important in partial differential equations, things like the wave equation. So if we have, the motion of a guitar string, this is going to be written in terms of sines and cosines and oscillating quantities. We're going to need complex functions. The heat equation, this comes up all the time in the heat equation. Again, the Fourier decomposition that we use to solve the heat equation is naturally written in terms of complex variables. This comes up in fluid dynamics, so potential flows. It comes up in quantum, so the Schrödinger equation natively is a complex valued, is a partial differential equation in terms of a complex valued wave function. Electromagnetism, the electric and magnetic fields can be thought of as the real and imaginary components of a complex function. So really, these are not imaginary at all. They come up all the time in the physical world. Now, part of the reason this is so confusing, and it still is, and it has been for hundreds of years, is because even though when we write down the mathematical solution of ordinary and partial differential equations, we get complex valued functions all the time, everything we have ever measured in the real world are real valued. I can only have a real valued angle theta. This can go from minus pi to pi, but it can't be I pi. Same thing with the velocity of this mass. That is a real quantity in terms of real meters per seconds. And so that's still kind of one of the things that's a little bit confusing, is trying to really disentangle how everything we ever measure in the real world is real, but under under the hood, kind of in the mathematical representation of these things, we need complex numbers to write them down. And I think a lot of this can be understood in terms of this complex exponential function. I'm going to come back to this over and over and over again. This function e to the I theta. So Euler's formula, Euler wrote this down, and it's one of the most important formulas in all of math, is e to the I theta can be written as cosine of theta plus I times sine of theta. And so essentially, e to the I theta for a real valued or imaginary, let's say for a real valued theta, this is a complex number that has a real part given by cosine of theta and an imaginary part given by sine of theta. And so all of these oscillating quantities here, like this mass on a spring or this oscillating pendulum, I could think about the position of this pendulum or the position of this mass as being given by the real part, this cosine of theta. And we know that the velocity of the pendulum, the theta dot or the y dot of these quantities are 90 degrees out of phase. Those are the sine theta, the imaginary part of this function. And so again, everything we ever measure is written in terms of these real numbers, x and y, but those are the real and imaginary part of a complex valued function. Okay, good. So we're going to be covering this again, 12 or 13 lectures on this. We're going to get pretty deep into how to do calculus with complex variables, differentiation and integration. We're going to talk about special functions of complex variables, z. But today I really want to get into, how do you actually manipulate these quantities? How do you do simple things like addition, subtraction, multiplication, division? How do you write these complex numbers in polar coordinates? And at the end, I'll give you kind of a roadmap of where we're going to go with this short lecture series. Okay, good. So I think at this point, what I'm going to do is just go into, basic things like how do you do addition and subtraction. So let's just get started. So addition and subtraction. And I'm going to say, let's say that we have, z1 equals x1 plus iy1, and we're going to say that z2 equals x2 plus iy2. Good. So addition, subtraction, if I have, z1 plus or minus z2, then that is going to equal x1 plus or minus x2 plus I times y1 plus or minus y2. So if I add two complex numbers, z1 plus z2, the real parts add and the imaginary parts add. And if I subtract two complex numbers, z1 minus z2, then I subtract the real parts, x1 minus x2, and I subtract the imaginary parts, y1 minus y2. Very, very simple. If I do, let's say, multiplication, I'll do multiplication and division. So multiplication, this was addition, subtraction. Multiplication would be z1 times z2. And we're going to just multiply this out. So we have x1 plus iy1 times x2 plus iy2. And we know that that is going to equal. So just like in algebra class, you multiply every single pairwise combination and add them up. So you get four terms, x1 times x2 plus x1 times iy2 plus iy1 times x2 plus iy1 times iy2. And we're going to collect all of the real parts and all of the imaginary parts. So I get x1, x2. That's a real number. And iy1 times iy2. Remember, I squared is -1. So that's just minus y1 times y2. So those are the two terms that are real. Plus, there will be two terms that are imaginary. And that is x1 times iy2 plus y1 times x2. So x2, y1, and those are both imaginary. So this is how you do multiplication with complex numbers. I'm going to show you that this is actually way easier to do using the polar coordinate representation of these numbers, but I'll get to that in a second. Let's say we do division. Okay, so division would be, let's say I take z1 divided by z2. So that's x1 plus iy1 divided by x2 plus iy2. And again, from your kind of high school or middle school math class, you probably remember that if you want to get rid of a complex number in the denominator, you multiply on the top and the bottom by its complex conjugate, by x2 minus iy2, x2 minus iy2. And when you do that, the term on the bottom becomes a real number. So if you expanded this all out, just like here, you would find that this equals, on the denominator, this equals x squared minus I squared, that's minus minus, that's plus, y squared, and this is x2 and y2. And on the top, I'm just going to say that this is z1 times z2 complex conjugate. And we define complex conjugate by this over bar. I'll write this down in a minute just so that you know what that means. And so this is z1, z2 bar over. This quantity here is kind of the length or the size of this z2, the norm of z2 quantity squared. Okay, so now I'm going to define what this means. Just make a little note here. Note that z bar equals x minus iy is the complex conjugate, and the length of a complex number z is equal to kind of its radius, which is x squared plus y squared square root. Okay, good. Good. So now what we've seen essentially is that we can do, all of the basic things. We want to basically be able to do algebra with these complex numbers. We can add, we can subtract, we can multiply, divide. You can multiply these by a constant, 5 times z. You just multiply 5x plus 5iy. And we did this in this kind of Cartesian coordinate system where you have the real and the imaginary part. But it turns out it's actually way, way easier to do multiplication and division if instead of writing it like this, you write these numbers in a polar coordinate system. So I'm just going to do that really quickly. I'm going to say that this equals, instead of x plus iy, we're going to say that this equals some radius. Maybe I'll derive this first. Okay, this is going to be some radius times an e to the I theta. I'll tell you what this means in a minute, but let's actually just draw this here. So the idea is that any complex number, x plus iy, can be written in terms of the real part of z and the imaginary part of z, and we can put these on coordinate axes. We can have a real axis and an imaginary axis that are kind of perpendicular to each other. This is called the complex plane, and usually I'll denote this by this kind of script c. And any number z that I want to represent, any number z that has a real part and an imaginary part, essentially the real part is its position in this x-axis, and the imaginary part is its position on this y-axis. So x in the real direction, y in the I direction. Let's say this is kind of the, I direction here. But of course, I can also represent these in terms of polar coordinates. Just like, normally I can represent a Cartesian vector x plus, x comma y, I can also represent this in terms of a radius and an angle theta. So if I do that here, I would say that the radius is r and the theta, the angle is theta. So I can just as well represent this complex number in terms of a radius and an angle theta. And the way that we write that is r times e to the I theta. And I'll explain why this is true in a minute. So essentially, if this is the angle theta of z, then we know that this position here, this x, is r cosine theta, and this y direction is r sine of theta. And remember from Euler's formula, e to the I theta is cosine theta plus I sine theta. So I can write this r cosine theta plus I times r sine theta as r e to the I theta. This is how we write this in complex polar form. Now I'm going to derive this in the next lecture. So essentially what we're going to do is we're going to take the Taylor series for e to the, let's call it e to the z, and then we're going to plug in I theta in for z, and we're going to find that all of the real parts add up to cosine and all of the imaginary parts add up to sine. So just take my word for this right now. This is called Euler's formula. Again, one of the most important formulas in all of mathematics, Euler's formula. And this is, we're using this kind of to write down this complex number in polar form. But what I really wanted to show you is that complex multiplication is particularly easy when we write it down in polar forms. Let's do that. Let's say that, again, I have a few vectors, and I'm going to use different colors for these. So let's say I have some vector, let's call this z1. And then I have another vector that is, let's say, z2. And I want to multiply these. And I'm going to say that z1 equals r1 e to the I theta 1. So this is theta 1, and its length is r1. And z2 is going to be r2 e to the I theta 2. So again, the length of this vector is r2. That's its radius in this, if I had a circle, that would be the radius r2. And this has a angle theta 2. Now, if I multiply those two quantities, maybe I'll do this in blue here. So I take r1 e to the I theta 1 times r2 e to the I theta 2. That is going to, by just multiplication, be r1 r2 e to the I theta 1 plus theta 2. And so this is, I think, what's really, really neat is that in polar coordinates, it's instead of multiplying this all out and collecting the real and the imaginary parts, which gets to be kind of a pain, if I multiply two complex variables that are already written in polar coordinates, then their radii multiply, r1 times r2, like the new vector that I'm going to get out of this. This is, let's say, z1, z2. The radius of this is going to be r1 times r2. So those multiply, and the angles, the angle of z1 and the angle of z2 just add. So this third angle here is theta 1 plus theta 2. So this is e to the I theta 1 plus theta 2. And that's just a property of how exponentials multiply. If I multiply two exponentials, then the arguments just add. So e to the I theta 1 times e to the I theta 2 is e to the I theta 1 plus theta 2. So that's kind of nice. Okay, so multiplication, and you could kind of verify that this is also true of division. This is, if I wanted to divide these quantities, this would be r1 divided by r2 times e to the I theta 1 minus theta 2, something like that. Okay, so it's way, way easier to multiply or divide when I think about my complex numbers in this polar coordinate system. And I mean, this is also going to be true when we do physics, when we do ordinary differential equations and partial differential equations, just like I showed you down here. It's going to be very, very natural sometimes to think about, instead of writing things in real plus imaginary part, just to think about it in terms of of, this kind of polar form e to the I theta. That's going to be more useful when we think about the wave equation, when we think about oscillating variables in physics as well. Okay, good. Yeah, so let me see, what else do I want to tell you? Maybe I'll tell you what's coming next. Okay, so this is just the very, very, very basic tip of the iceberg, where we have talked about why we care about complex numbers. They come up all the time in any kind of oscillating solution of ordinary or partial differential equations. We've talked a little bit about what these complex numbers are. Complex numbers are the necessary ingredients to the solution of polynomials. Things like, if I want a square root of -1, I have to introduce this I. We've talked a little bit about the how. How do we add? How do we multiply? How do we divide? And specifically that it is easier a lot of times to do this multiplication and division when we use the polar form, this radius times e to the I theta. Maybe I'll just write this out really, really, really explicitly, that this, z equals r e to the I theta equals r times cosine theta plus I sine theta. And again, r cos theta is the real part x, and r sine theta is the imaginary part y. These are totally equivalent representations of this complex number. And what's coming next, kind of the next piece of all of this is, let's say next, we'll be thinking about functions of a complex variable. So functions like, what if I take, z quantity squared? If I take this complex number z squared, you can verify that this will equal, what is it going to equal? X squared minus y squared plus I times 2xy. That is a complex function z squared. And you can write down lots and lots and lots of interesting functions that are going to be useful in the solution of ordinary and partial differential equations. Polynomials like z to the n. You can write down sine of z, cosine of z, e to the z. We've already seen e to the I theta. So all of our favorite functions from real analysis, from real valued function theory, like sine and cosine and exponential. Logarithm is a hugely important one, log of z. I give it a capital L to distinguish it from the real valued log of z. All of these can be extended to be functions of a complex variable, not just a real variable x, but a complex variable z. So this is just one example here. And what we're going to find is that there is a huge class of what are called analytic functions, like z squared or z to the n or e to the z, sines and cosines. These are analytic functions. And what that means is that the real part and the imaginary part, this function of x and y and this function of x and y, are solutions to Laplace's equation, del tron del squared of, let's say, the real function phi equals 0. And this, again, is hugely important. These are the solutions, the building blocks of electromagnetism, of the heat equation, of the wave equation, of all of partial differential equations. Much of partial differential equations is built on Laplace's equation. And the solutions of Laplace's equation are the real and the imaginary part of these analytic complex functions. So this is all coming up in the next, let's say, 12 or 13 lectures. We're going to talk about how to do calculus, how to define functions of complex variables, how to do calculus on those functions, derivatives and integrals, how to understand how these are solutions of Laplace's equation. We're going to derive Euler's formula for the Taylor series e to the, of e to the I theta and all of that. So again, this is about a 2-week course. The first week, I would say, is essential to understanding how complex variables work. The second week is interesting but pretty advanced material. So highly recommend the first part, but if you're interested, stick around for the whole thing. All right, thank you.